Okay, so today we're going to extend the functionality of our finite volume method to include heterogeneity. Oh. Let's see here, what's going on? So remember, if we have two cells, finite volume cells, we use this 2-point flux approximation. So normally we would, basically compute the transmissibility between the two centroids, right? Is everybody able to get that on assignment 15 and get it to work? It's not too hard, right? I'm going to go over the rest of assignment 15, like the residual calculation and other things, because some of the code's written a little strangely, maybe, for you guys. So I'll go over it in just a second to kind of make sure you understand everything. But implementing the actual transmissibility is not difficult, right? So what we'll do when we have a heterogeneity is we're basically going to break up the transmissibility into two pieces, right? So basically the transmissibility between, we'll call this node I and this node J, and we'll call this the face that they share. So we're going to compute the transmissibility between the node I and the centroid of the face, and then between the face and node J. Okay, and so basically just instead of before you had K over mu AF divided by I think I wrote Dij. So now you're just going to split that Dij up into two pieces, like between the node I and the centroid of the face. Maybe we'll call that Di, and then between the face and node J, we could call it Dj, right? So there's basically just two distances that then we'll have, so this would be like Di, and then you have Tj, Ki, Kj, mu, AF, Dj. So this is Tj, okay? Now the only thing is the AF is the cross-sectional area of this face, right? So, there's some depth into the paper, right, into the board. And the depth is usually identified per cell, right? So it could be that, one face has a different, there's like different varying depths, right? So we do need to average those depths and use them in both, right? So AF is going to be, what I'll call AI plus AJ over 2. Okay? So we're going to average the depth. I shouldn't. Yeah. So this is the cross-sectional area. So the length will be the same, but then multiplied by the depth of each cell. So you'll have an AI and a AJ, and then so then with that, the total transmissibility is just the harmonic average of the two. So not too much change from before, just a small extension, right? And that allows us to then compute transmissibilities with varying properties, okay? So then the other thing is, how do we deal with wells and finite volumes, right? So basically it's all the same, right? We have, just like before, we have a well model that's like P of the well minus P of the cell, right? Where this is J is the productivity index. And if you remember, J basically has this REQ that in a finite difference setting, it's basically a function of delta X and delta Y, right? But now we don't necessarily have delta X and delta Y because in general are polygon, we have polygon elements. I know I've drawn triangles here, but this REQ calculation will work for any shape element, right? Quads, irregular polygons, whatever, irregular triangles, not just right triangles. Now we will have to get smarter about our flux approximation if we have irregular elements, right? Because of what I mentioned last time, you don't have that normal condition, right? But for REQ, basically all we have to do is, take the square root of the volume divided by pi divided by the depth of the cell, okay? And of course, volume is area times depth. So if you have the cell area, then this is just the area of the cell divided by pi, right? And understand that the area of the cell is not the cross-sectional area of a face, but rather literally the area of the triangle itself, right? Whereas AF is the area of the face in which the fluids are transporting through. Okay? So that's really all we need. I mean, everything else, the entire productivity index calculation that we used in finite difference method holds. It's just the REQ is now this, okay? And in the code that I wrote for assignment 15, which I've just extended for assignment 16, I'm already computing, I don't know if you noticed, but there's already a class attribute called cell areas, right? So I've already computed the cell areas for you. Done most of the topology part of the code, right, already for you. So let's take a look at the code. So first I'm going to just describe assignment 16 quickly. Not that hard, but I'll describe it, and then I will go over the other part, because this assignment shares most of the. In fact, when I wrote my solution for assignment 15, I already implemented everything. Like, this is my assignment 15 also solution, right? Because it already has the heterogeneous transmissibility in there. Of course, the heterogeneous transmissibility will reduce to the homogeneous transmissibility in the case that you have equal permeabilities, right? So, so everything else is the same in this code, but for really all you have to do is to implement your REQ condition and implement the heterogeneous transmissibility, right? So basically there's just two functions you have to complete. So I've already written the function compute productivity index, and in fact all I did was steal it from my old finite difference code and then just implement a new REQ, right? So see where that line's commented out for REQ? You just have to implement that. Not too hard, especially because the formula is real simple, right? So you implement that will compute the productivity index for you appropriately. Then you need to basically update your compute transmissibility to handle heterogeneous permeabilities, right? You do not need to update compute boundary condition transmissibility. That doesn't change, right? Because you're just going from the cell center to the centroid of the face of the boundary cells. And then the last thing you need to do is just in the compute residual, you need to add a couple of lines for updating the wells here, okay? So that's what you have to do to complete this assignment, but let's go over the entire code quickly so that in case you didn't have a strong understanding of what's happening. In particular, in this compute residual, like where we're computing the actual residual form, okay? So you remember I told you that I've kind of switched the data structures from using NumPy to using JAX, because what does JAX give you? It gives you automatic differentiation, And it gives you also, even though we're not really using it here, it gives you the capability to run on an accelerator like a GPU. So you could run this code, this very code, on a GPU and get, I think there would be 1 or 2 lines that you have to specify at the top to basically specify the target device. I think it would literally just 1 line to tell JAX that you want your arrays to run on the GPU. But other than that, everything will work. I don't know if you guys ran this, really realized, if you ran this code, like really realized how fast it is. It's blazing fast. It's like, if we ran bigger problems, I would bet this code is much faster than CMG. And then we can throw it on we can also throw it, obviously for the same problem, right? CMG has a lot more capabilities, compositional flow and everything. But you tried to solve this exact problem in CMG, this code is going to be much faster, most likely. And we could run it on a GPU and get even more acceleration. So, do you guys know kind of what's different about CPU and GPU computations? And like why you can, let's before I go into this, let's go back to the, just talk about that for a second. So let's say I have 2 arrays. X, right, is an array x1, x2, x3, xn, right? And then I have an array y, x1, x2, y1, y2, y1, y2, y3, yn, right? So in NumPy, if I set up these 2 arrays and I type x times y, right, then it does an element-wise multiplication. And the reason NumPy is much faster than Python, right, is that element-wise multiplication, what I'm saying is the reason using NumPy data structures is much faster than using Python lists to do the same thing is because the actual number crunching part of this array multiplication is all written in C. There's just like a very small Python wrapper around the C code where the C code is actually, it's compiled code that can then do this multiplication. And if you went and looked at the C code, what you would see is that there's like a for loop that loops over the elements in sequence, right? So it's like for I in range of n. Let's just write some pseudocode. It would be something like for I in range n, result is equal to xi times, result I, right, is equal to xi times yi. So something like that. In other words, the computer first does x1 times y1, and then it does x2 times y2, and then it does x3 times y3, right? So in sequence like that. That's how a CPU operates. The GPU, on the other hand, GPUs were originally invented like in the late 90s. The reason they're called GPUs, even though we mostly use them for number crunching these days, the reason they're called GPUs is graphics processing units, right? They were originally designed for first-person video game. Any gamers in here? Yeah. I'm not really a gamer. My son is, though. But I remember Doom and all those games when they first came out, right? But basically, they're designed to simultaneously render pixels, right? Just basically, you got to render all the pixels on the screen 40 times a second, really fast, all at once, right? To give that kind of smooth first-person video game feel, right? And now they're almost like photorealistic, right? It's like almost like it looks totally real, right? But anyway, somebody in the early 2000s, some folks, some computer scientists realized that we can trick the GPU into thinking it's rendering pixels, but instead have it do number crunching, right? And of course, then later NVIDIA basically released CUDA, which is like a subset of C programming language that can, basically program GPUs for doing numerical computations. But again, the benefit is that they're designed to render all the pixels at once. So in this context of array computations, they're designed to render or do all of the array multiplication at once, right? So instead of doing x times y and x1 times y and then x2 times y and then x3 times y, they do them all at once. So x times y1, x1 times y1, x2 times y2, x3 times y3 are all done simultaneously, right? As long as the entire arrays can fit in memory. And so that's where you get huge advantage, right? And any discrete equations, ultimately, it's just a bunch of vector-vector or matrix-vector products, right? And matrix-vector products are just, one at a time vector-vector products, right? Just multiplying vectors together. So that's what GPUs are really, really good at, really fast at doing these kind of things, right? So if you took this code and ran it on a machine that had a GPU, which could include some of you have new Macs, right, with the M4 chips, you can actually download a special version of JAX that's been compiled to run on a Mac. It's called JAX-Metal, for Apple Metal, and you'd be shocked at how fast your code can run. So if you have any old NumPy code laying around, and you want to accelerate it, if you have a new Mac and you want to accelerate it, you can basically just change your NumPy arrays to JAX arrays, and you'd be shocked at how much faster your code runs. So anyway, back over here. Let me increase the font a bit. So most of the code at the top is just kind of utility functions that are just doing stuff. I have this parse inputs functions, which reads in all the functions, and a lot of it's for finite volume method is topology information, right? So I don't know if you did you look at the input deck and see how the kind of input is structured for these types of problems? So now I'm actually prescribing the actual faces that the boundary conditions are applied, and the discretization is basically consists of a bunch of topology information, right? So the nodes, these are just the XY values of the nodes, the corners of the cells, right? And then the faces basically define, so these faces are defined. So this first one, that's, face 1 is defined between node 0 and node 1. Face 2 is defined between node 1 and node 5. Face 3 is defined as between node 0 and node 5, right? And so then all the cells, so cell 1 is defined of face, it consists of face 0, 1, 2. Cell 2 consists of face 3, 4, 5. And this is all consistent with the picture at the top, right? So that's all the topology information. Now, normally this would come from some type of mesh generation software. You wouldn't hand specify like I did, but I just wanted to see how it works, right? So you'd have some mesh generation tool that you'd mesh your domain with, and then you get to gather that topology information from it, and then that's how you use it to do various things. So a lot of the functions at the beginning are just kind of helper functions. So I read in the things. Basically, if you look at the structure of cell nodes, that basically gives you the XY locations in a nested list format for each cell. So the kind of first nested list and the outer list would be XY location for node 1, 2, and 3. And then there's another list and another list, or it's a nested NumPy array. Cell areas are exactly what they sound like. It's the areas of those cells. The centroids are the centroids of the cells. The neighbors are just neighborhood lists that basically, so that's what you need to loop over to compute the transmissibilities, right? So if I want to know the neighbors of cell 0, it has a neighbor 4 and a neighbor 3, right? See, the ones that share faces. A neighbor is a cell that shares a face, right? So cell 0 shares face 2 with cell 3 and shares face 1 with cell 4, right? And so when you have to compute the transmissibilities, you're computing it over the neighbors, right? And so that is basically a list that, for cell 1, so for cell 0, that list is like 3, 4, minus 1. There's minus 1 in there because my arrays have to be rectangular, right? And the minus 1 is just a dummy placeholder that basically says, because my array has to be rectangular, but some of the cells have 3 neighbors, right? So like this interior cell 10, it has a neighbor 6, it has a neighbor 7, it has a neighbor 13, right? But the ones on the boundaries would only have 2 neighbors, right? So that's why you have this nested list, and there's like, if a neighbor only has 2 neighbors, in the third placeholder there'll be a minus 1, which is just a dummy value that means, there's not really a neighbor here, right? This one only has 2 neighbors, okay? So we read in, do a lot of, same thing as before for permeability. We create a list of permeability, so there's one for every cell. Same with depth and porosity. I also compute the face lengths and face centroids. Those are useful for those boundary conditions. Hopefully you probably use those face centroids in the boundary condition implementation of transmissibility. And then now in this one, I also have some well stuff that happens up front. So basically, I already solved the problem of finding which grid index the wells are in. So the wells are identified by their location, like XY location on a map. But then we have to figure out what cell they're in, right? So in this problem, if you look at the picture, the nodes are in, the wells are in cell 7 and cell 14. And the code that does that is already there, so you don't have to, because it's a little bit different for, it's easier, we use a different technique when you have a rectangular grid, but when you have polygons, then you have to do something different, right? And so I'll show you that in a second when it gets to it. But basically then, I have these class attributes, rate well grids, those are the indices of the grids, rate well values, those are like the injection rate or production rates, and the rate well productivity index. I go ahead and compute those by calling compute productivity index. Of course, this function is not complete right now because REQ is not there, but there's a short fix to do that. In the event that there are no wells, I just have this other function that says assign dummy well values, which assigns 0 to everything. Because you'll see later, when you write the code, the most efficient way to write it is just in the cases where there are no wells, you basically just add 0 to the overall transmissibility. Right? So it just assigns dummy values in the event there are no wells. Okay, and that's what this does. You can see these rate well grids just becomes 0, rate well values is 0, rate well productivity index 0. Same thing with BHP well grids, BHP well values, BHP. They're all just zeros. Okay, so function that applies the initial conditions. This is my function, check input and return data, that basically checks to see if it's a string, a list, or a constant and creates an array from it. This is my function that computes the well index locations. What I do here is I use a special function from matplotlib called matplotlib path. So basically then I can specify the nodal locations of the polygon. It creates a path, and then there's a function, once you create the path, there's a function that says contains point. So then you can just stick the point in there and it returns true or false, right? So basically then what I'm doing is looping over all cells, creating a path via the nodes of the cells, and then checking to see if the well location is in that cell, okay? Here's my compute productivity index. Again, this needs to be completed by adding the REQ term. This computes the cell neighbors. Again, these are not JAX compiled because they're only done once up front. This is just stuff that's done once, like at the front, at the beginning of when you instantiate the class. So basically just computing topology. There's not a lot to be gained from compiling those functions. It's easier to just write them in like pure Python with for loops and whatever, again, because they're only done once. When we get to the residual calculation and computing the transmissibilities and different things, that's where we want to be fast, because in a nonlinear problem, this is a linear problem, but it's written as if it were a nonlinear problem. And in a nonlinear problem, you would have to basically compute that residual and Jacobian every step in the problem, so you want it to be as fast as possible. Right? So also, computing the boundary condition cells, basically those are the cells in which you've defined faces that you're applying boundary conditions to. So here's the compute transmissibility that you would have written last time. Now you notice on this one it has this thing at the top, this JAX JIT. What JIT means, just in time. It's a compilation step, right? So the first time you execute this function, it compiles it to assembly code that would be equivalent to like if you wrote it in C or Fortran. And when I say, sometimes you'll hear me say that like as fast as C. Well, the reason I say that is because nothing is faster than C. Nothing is faster than C or Fortran. I mean, those are the two like lowest level languages you can, but no one really uses Fortran anymore. Certainly not for new projects. Right? But so basically, this gets compiled into a function that's as if you wrote it in C. Right. Here's the boundary condition transmissibility. Here was my implementation. I think you guys had to do that for assignment 15. It should look something like this. Accumulation, same thing. All of these are compiled. And so here's basically where I compute the neighbor flux. And so there's three arguments. By the way, this partial decorator JIT thing, what that does is it basically, you see this one that says static argnums. The first argument, because these are methods of a class, they're not pure functions written outside a class. The first argument, self, that's the thing that passes in class attributes and other things. This basically compiles it as if those are static when it's called, so meaning they don't change, right? So the cell number, the neighbor number, the face number, and the p vector could change every time this function is called, but self never changes. In other words, and self is again where the class attributes are stored. That's like the topology information, the permeability, right? Those are properties of the grid. They don't change after we find them initially, right? They don't change with any function call, right? So here, basically, we're just computing the flux between the cell and its neighbor across a face, right? And I have to pass P, I have to pass P in so that I can, basically compute PI minus PJ, or PJ minus PI, rather, right? So, and here's where those minus ones come into play. So you can see, basically, there's this variable valid that is a true or false, right? Basically, it checks if the neighbor index is -1, then this is not a real flux computation. Return 0, right? So that's what JNP where does. It basically says, if this condition is true, or in this case, if it's not equal to -1, the dummy value, that means it has a neighbor. Then I'm going to compute the transmissibility. And again, cell, neighbor, and face are just numbers, right? They're like the I's and J's. So the cell index, I'm computing the transmissibility between the cell index and the neighbor index across the face index, right? And then multiplying by the conversion factor and PJ minus PI, essentially, right? So this computes one flux between neighbors, okay? And this is a compiled argument, or a compiled function. So then I compute what we call the cell residual. So basically this sums those fluxes over all neighbors, okay? So here I have, a neighbor, the neighbors are the neighbors of the cell, and the faces are the faces of the cell, right? And I compute this T, which is like the sum of the flux across all neighbors, right? Everything coming in or out of a cell, right? And this VMAP function basically is a vectorized, it vectorizes a function across a list. It's sort of a functional operation. So basically what I'm doing is I'm vectorizing the function neighbor flux. So neighbor flux is a function that's intended to only compute the flux between one cell and one neighbor, right? And so I vectorize it or map it across all neighbors, right? And so the first argument to this thing must be a function, and the function is neighbor flux, but the function neighbor flux is got four arguments, right? Cell, the neighbor, the face, and the pressure vector, okay? But what I want to do is I want to map that I'm going to hold the cell fixed and hold the pressure fixed and map it across all neighbors and faces, okay? So in this case, I create a new function that's now, so this whole first argument is really just a new function because I used a lambda function. I kind of explained that in the text of assignment 15, right? So I'm binding cell and P, and I'm allowing N and F, neighbors and faces, to be free, and then I'm mapping this function over all neighbors and faces of cell, right? So that basically, so that gives me the output of this first thing is a new list, which is the transmissibility of each thing coming into the cell or out, just defined by the sign, right, positive or negative. And then the dot sums those all up into one, right? So then I just have one value, T, and the same thing, B, I don't have to do anything fancy. I'm just calling compute accumulation for the cell, and then P of the cell plus P old. So P old is the value of the pressure from the last time step, right? So this is like P is really P in plus 1, and P old is P in, like the old time step, divided by delta T, right? Because this is like a finite difference derivative in time, okay? So this gives me the cell residual, right? B minus T, right? That's the residual value of a cell. So then I just have to map that across all cells, right? And then I get the total residual. And so also this function then applies the boundary conditions to the residual by computing the transmissibility just between the cell and the boundary face. And then you have this update, which I'll talk about in a second, right? So then you have compute residual. Remember what the residual vector is, right? It's like that, we write down essentially the discrete form of conservation of mass, and it should equal 0 if mass is really conserved, if we have the right pressure values, right? But if we just guess some random pressure values, it's not going to equal 0. And that out of balance part is what we call the residual. And then we can use a nonlinear solver to drive that residual to basically judiciously choose how we change P such that we drive it to 0, right? So the residual, we start with just an array of zeros initially, and then we map that cell residual function over all cells. So that's what we're doing. The first part of this basically, creates a new function that maps cell residual over some argument, and then the argument is all the cell numbers. So that maps the residual, basically returns a vector over all cells, right? So then the residual then it's a vector where each entry corresponds to like the out of balance part of that cell equation, right? As a function of P. Okay, so then we loop for the boundary. We loop over the boundary conditions, also doing this apply boundary condition for that. Now, whenever in JAX, there is one kind of caveat. So we're all used to, like, if you had a NumPy array, right? Remember, residual's an array, and let's say in NumPy you wanted to change the third element, or the 3 index element. You wanted to add 3 to it, right? So I'm going to add 3 to the third element, right? That's how we would do it in NumPy, okay? In JAX, we have to use a little bit different syntax to do the same thing, right? I mean, I guess a lot different syntax, but it results in very efficient code when it's compiled. So in JAX, what we do is we say residual at 3, add 3, or 3, right? So those two lines are equivalent expressions between NumPy and JAX, okay? And then of course they can also accept lists. So in NumPy, if you wanted to add to cells 3 and 7 the values 3 and 10, right? You would do it like that, okay? So no different here. In JAX, I can also feed this a list, 3, 7, 3, 10, like that, right? And so they're just, if that's for adding, if you want to add to the value, right? If you wanted to set the value, then you change this to set, and that would be equivalent to this, right? And if you want to subtract, then you just put a negative sign in front of the argument in the last thing, right? Subtracting is like adding negative, right? So, yeah. So you still use add, but you subtract. Yeah. All right.
Is that argument the same, or we can write the first one instead of the second?
No, you cannot. In JAX, you cannot write this. It'll give you an error. In fact, the error will tell you to write it like this. Yeah. Yeah. So if you do it just out of you forget or something, I think I did that when I was working through it myself. I just kind of fell back to my old NumPy code and wrote it the first way, and it'll throw an error that tells you that you have to use the second method in JAX. Okay. So, most of the function calls in JAX are the same. Some, if you want to compute the sign of an array, JNP.sign. But this is one area where you do have to use a different syntax to do things like that. So, so that's all I'm doing up here. I'm returning, the residual at cell, and I'm adding the boundary condition term to it. Okay. So you'll need to use something like that to add for your wells, right? So there'll be something like that where you have to add a term. I'll rough it out for you. It's going to be something like, you'll have to do it, so residual at well, let's just do rate well grids first. So residual at rate well grids, residual equals residual at rate well grids add self rate well values, something like that, right? So that would how you do it for rate wells. I'll leave it to you to figure out how you would do it for BHP wells, right? So for BHP wells, the rate is J times the pressure difference between the cell pressure and the bottom hole pressure of the well. Right? Okay? So, and again, so that's how, I'm computing the residual vector, basically mapping the cell residual function over all cells, and then just looping. This is a JAX for loop, so the for loops are a little bit different in JAX, but this is a JAX for loop looping over the boundary condition cells and applying the boundary condition function, right? Now that I think about it, could have easily wrote this as just another VMAP function where you're just mapping apply boundary conditions over the list of boundary condition cells. You wouldn't even need a for loop. You could just use VMAP there too. Okay, so then compute Jacobian. How easy is that? Right? Remember all the headache it is to figure out the topology structure of a matrix, with all the -1s and where the boundaries are and all that stuff. Hell of a lot easier to write it that way, right? And then in this case it's a linear problem, right? So we could create the matrix, but if it's truly a nonlinear problem, like if you had pressure dependent permeabilities or anything like that, where your Jacobian is a function of pressure itself, then the only thing you can do is to do it like this, right? And in this case, we are forming the full matrix because I just wanted to be clear for you guys. But there's also what is called a matrix vector operator in JAX that you can use with a solver, so that you don't ever have to actually form the full matrix. Because remember that if you look at the form of that Jacobian, it's mostly zeros, right? and then previously we used like sparse data structures and everything. Well, there's a way to formulate this as a matrix vector product operator, and you don't ever actually have to formulate the whole matrix, right? But we did it this way. I wanted to be like clear so that it kind of looked like the notes that I wrote, that we're forming a matrix J and then solving a nonlinear problem to find delta P, right? So that's what we do in this solve one step. And basically, we make a copy of self.p and set that to a value p that we're going to iterate on. And then we compute the Jacobian using p and self.p. Self.p is like where we store the old value, right? So remember, the two arguments to compute Jacobian are p and p old, right? So self.p is where we're going to store like the old converged solution, right? And so first thing we do is compute the Jacobian, and because it's a linear problem, we never have to compute it again. We just compute it once up front. If it's a nonlinear problem, we'd have to move that compute Jacobian inside our loop and compute it every time, okay? We compute the residual once up front just as our starting place, and then first thing we do is compute the norm of the residual. So you get like a scalar value. Again, if we have an exact solution, if we know the exact p, what's our residual vector expected to be? 0, right? 0 vector, so it's 0, 0, 0, 0, 0. What's the norm of the 0 vector? The L2, the default is the L2 norm, so like the square root of the sum of the squares of the elements. So if I have 0 squared plus 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 0 squared, square root of all that, what is it? It's 0, 0.0, right? So our norm, or R norm, becomes a condition on which we can terminate our loop, right? Because if it's a very small value, then we're close enough to saying that we have the right solution, right? So the first thing we do is compute that norm. I have a little function in here just to print out some stuff so that you can watch it converge. I'll show you in just a second. But that's not that important. But here's the kind of important part. It was basically, so, you know, I use a for loop so that it doesn't get stuck in an infinite loop if it's not converging. You know, the maximum it'll try is 100. If you watched it before, how many steps does it take?
5.
No. Those are time steps. It's a linear problem. It converges in one iteration every time. So, and I'll show you that in just a second. But basically, yeah, when the R norm, when this norm value is less than some tolerance, which the default value is like 0.001, I'm sorry, 0.01. Right? Remember, our pressures are like on the orders of thousands. Initial reservoir, you know, the boundary condition is 2,000. So I don't think we need to set the tolerance to, you know, 1 e to the minus 6, even though the norm is very small initially. I mean, after one step, right? So if the R norm is below the tolerance, then we break out of the loop, right? So that's what that break statement does. Otherwise, we solve this linear problem, J and minus R. You know, so like this is the argument. You know, this is the A matrix, and the minus R is the B vector, and we're solving for X, or in this case, delta P. And then we add delta P to P, and we compute the residual again, and we loop, right? So last thing we do is compute the residual again with this new value of P, and then we loop around, compute the norm, and do it again and again and again, right? And if it's a nonlinear problem, it might take several iterations to converge, okay? But here you'll see it literally just takes one iteration each time and it converges. And then once it converges, when we're out of this loop, we have a converged value of P. We set that to self.P. That becomes P old, right? And then we do it again in time, right? So this solve one step, you know, ends with setting the converged value to the old value. And then solve just marches in time, calling solve one step each time, right? So let's watch this thing. So if I go down here, and then run all. So what you see there is that first print of the residual is the residual. Remember, we compute the residual here. Before we enter the loop, we compute the residual. And then the first thing we do is compute its norm and print it. So this first value is it's the value of the residual before you've even entered the loop, right? That's like the initial residual from your initial guess. Whatever the initial pressure is, right? So initially the residual is, this big number, and then it takes one step and it becomes that small number and it breaks out of the loop, right? And then so, this is over 10 time steps, but, we could run it for 100 and watch how fast it is. No different. I mean, most of that time is printing to the screen. Like literally no difference. And we could run it for 1,000, right? And it wouldn't matter. So yeah, JAX is cool. Especially if it's really cool if you already use Python and NumPy, because it kind of, you get a lot for free. Like you don't have to learn much new, Yeah, all right, so just to, reiterate what your objective is on this assignment, add REQ, square root of the volume over pi divided by the depth, or the square root of the area divided by pi. Add the implementation for compute transmissibility, where you're computing now the transmissibility between cell I centroid and the face and cell J centroid, and then using a harmonic average of those two, Ti and Tj's. And then add the terms you need to add wells to the residual in the compute residual calculation. Those are the three things you need to do to get this to work. All right? Go ahead and start. And yeah. I know I took up a lot. I thought it would take like 10 minutes. I took half of the class. So, maybe you won't finish that. I still think there's time to finish. But if you don't, just get it done by Tuesday. Tuesday we'll look at multi-flux approximations, multi-point flux approximations. So then you're going to truly have irregular grids. Oh, another thing I wanted to point out, sometimes, going back to the lecture where I started with this so-called weak form, right? So sometimes people think, right, probably in undergraduate reservoir engineering, when you derive the conservation of mass, you probably did it in a way that looked like a finite volume technique. You drew a control volume, right? And you drew a flux coming into the control volume, and then you basically said, the mass in this control volume is the things coming in or out of it, plus the accumulation, right? And then you just wrote down what those terms are. So you might tend to believe that there's something kind of special about conservation of mass, or that there's some marriage between these conservation of mass and reservoir simulation equations that we're using and finite volume methods, because you can kind of derive them from finite volume methods. But what I want you to be clear about is that the approach that I took of like developing this weak form will work for any differential equation. You can solve any partial differential equation with these same techniques, right? Basically, you develop the weak form, then you use a test function of 1, and that thing will result in a finite volume approximation. Then you still have to figure out like how to approximate your fluxes, but the point is you can use, this is a generic discretization technique. It's not somehow married just to conservation of mass, because we can derive conservation of mass in a way that looks like, you can start with a discrete control volume and kind of derive the conservation of mass, or you can go the other way. You can start with conservation of mass, develop the weak form, and get back the discrete control volume, right? But that same procedure will work for any partial differential equation. You can take any partial differential equation, multiply by a test function, integrate over the body, integrate by parts so that you generate that boundary term, set one as your test function, and you have a finite volume discretization method. You just have to know how to approximate your derivatives. And the 2-point flux approximation works for the grids that we're dealing with, but then we'll learn something more complicated next time. So yeah, just want you to be clear, this is like a generic PDE solution technique. It's not somehow married to reservoir simulation or specific to it. Right? Okay.